So, in the world of formal logic, there's this rule that's, well, it's both fascinating and honestly a little terrifying. It basically says that a single tiny contradiction doesn't just cause a small error. No, it can detonate an entire system of thought, proving that anything and everything is true. Today, we're going to dig into that rule, the principle of explosion.
I mean, just think about this for a second. What if one tiny paradox, a statement that's somehow both true and false at the same time, was all it took to prove that 1 plus 1 equals 3? It sounds completely absurd, right? But believe it or not, according to the strict rules of classical logic, it's not just possible, it's guaranteed.
All right, so first up, let's really unpack this destructive power. There's this kind of hidden rule deep inside classical logic that turns a simple paradox into an absolute catastrophe. And understanding that is the key to seeing why the whole system can be so fragile. In most fields, a mistake is, well, it's just a mistake. It's something you can fix and then you move on. But in classical logic, oh no. A contradiction is treated as the ultimate error. It's not a bug you can patch, it's a total system failure that brings the whole structure crashing down. Let's take a look at the mechanism that actually causes this. So, this mechanism that causes the whole system to fail is the heart of what we're talking about today, the principle of explosion. And trust me, it's every bit as dramatic as it sounds. This is the rule that lets one tiny little falsehood be used to prove literally anything. So the formal name for it is pretty cool. It's got this Latin name, ex falso sequitur quodlibet, and that translates perfectly to, from falsehood, anything follows. The rule is simple and, well, it's brutal. If your system has a contradiction in it, you can logically prove any statement you want, no matter how wild or absurd it is. Okay, so this shows the chain reaction. Here's how it actually works. First, you just assume a statement, we'll call it A, is both true and false at the same time. Now here's the clever little trick. From the statement A is true, you can logically say either A is true or the moon is made of cheese. That's a totally valid logical step. But since we also know that A is false, that first part of our or statement is out, which means the second part has to be true. And boom, just like that, you've proven the moon is made of cheese. Once that door's open, the entire system just becomes meaningless. So, when a system can prove that the moon is made of cheese and at the same time prove that it isn't, it enters this state that logicians call trivialization. It's basically the logical equivalent of a complete and total meltdown, where the whole concept of truth has lost all meaning. The endgame here isn't just a system with a few flaws, it's a completely trivial and meaningless one. I mean, think about it. If your logic can prove both a statement and its exact opposite, it's lost its entire purpose, right? Its job is to tell truth from falsehood, and now it's just useless. And this isn't just some abstract puzzle. This is real stuff. Back in the early 20th century, a philosopher named Bertrand Russell discovered a paradox hiding right in the heart of set theory, which is a foundation of mathematics. Because of the principle of explosion, this one single flaw meant that, logically speaking, the whole structure of math was useless. This crisis made avoiding contradictions an absolute #1 priority for every mathematician and logician out there. But that huge crisis led to a really radical question. People started asking, what if you didn't have to avoid contradictions at all costs? What if, instead, you could just tame them? And this idea led to the design of way safer, more resilient logical systems, ones that could actually handle a paradox without completely collapsing. The solution really comes from a totally new way of thinking. So you've got classical logic, where the only goal is to avoid contradictions. If one slips in, the whole system explodes. But paraconsistent logic, it takes a completely different approach. Its goal isn't to avoid paradoxes, but to isolate and manage them. It basically contains the contradiction, so it can't destroy everything else. And how does it do that? Well, it takes direct aim at our explosive little rule. And that, right there, is the key innovation. Paraconsistent logics were designed for one main reason: to reject the principle of explosion. By just getting rid of that one single rule from falsehood, anything follows, they let a system contain a contradiction without becoming trivial. The paradox gets walled off, and the rest of the system can just keep on functioning perfectly fine. And look, this wasn't some kind of fringe rebellion. Even foundational figures, guys like A.N. Kolmogorov, a real giant in logic, had their doubts. He wrote about his doubt in the intuitive clarity of the principle, ex falso sequitur quodlibet, which is a fancy way of saying that this rule everyone just took for granted, maybe it wasn't as solid as it seemed. So this brings us to one last really crucial question. Why would we ever want a logic that can tolerate contradictions? I know, it sounds super counterintuitive, but as we're about to see, it actually opens up some incredibly powerful new ways for us to reason about the world. So, why does any of this matter in the real world? Well, because paraconsistent logic is unbelievably useful. It lets us reason about evolving scientific models, which, often have temporary contradictions as new data comes in. But on a deeper level, it shows us something amazing. The rules of logic aren't these absolute, unchangeable truths. They're tools that we invented and that we can adapt to solve new problems. And that kind of leaves us with a provocative thought to chew on. We've just seen that one of the most core principles of logic isn't untouchable. It can be thrown out and replaced to create something even stronger. So, if the very rules of reason can be rewritten, what other absolute rules are just out there waiting for a fresh perspective? Thanks for joining us for this explainer.